let's start here. Um, go ahead and move this over here for now. Focus on this. All right. So today we're gonna take a look at the Riemann hypothesis. I don't actually know much about it yet, so we're gonna start with the basics, um, and I will sort of uh, talk about my thoughts as we go along. Um, so let's see. Um, so the conjecture is that um, all of the zeros of this particular function have real part 1/2. So it is a question about um, something, a function in complex analysis, um, specifically the zeta function, uh, which I will put this over here. So the zeta function is the sum of the uh, uh, 1 over n to the s, um, and goes to infinity. All right, and this is the zeta function. And then s is a complex number. So that means um, s equals a plus bi, where a and b are real numbers, and I equals the square root of -1. Okay, so then let's see. Now we know a few things about this series already. Specifically, Euler proved that zeta 2 equals, let's say, infinite sum of to from n equals 1 to infinity of 1 over n squared. That equals pi squared over 6. Uh, okay. And um, let's see what else. Okay. Um, now we also have here that zeta s is the product of uh 1 minus primes to the negative s power. Um, Now one thing I remember actually is um, when I was visiting the Santa Cruz campus, um, one of the I was talking to one of the professors there, and he showed me why this particular thing is true. But I don't remember specifically why it's true right now. Um, So, uh, oh, okay. So, one thing, um, is that, um, p to the, hmm, well, if we, try and combine, uh, fractions, okay? Or maybe that's the wrong. Oh, no, no, no. Okay, I remember what it is now. So we're going to group the um, zeta function slightly differently. We have it as 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so on. So we're just gonna rearrange it a little bit. Um, Specifically, we're just gonna keep the 1 over 1 to the s by itself, and then we're going to um, uh, group all of uh, the factors of the multiples of 2, and then the multiples of 3. But we got to be careful here, um, because we already have um, 1 over 6 to the s here. So we have to exclude the factors, the multiples of 2. So we get 1 over 3 to the s plus 1 over 9 to the s plus 1 over 15 to the s. And then we do the same thing for each prime along the way. So, um, and now the second term is always going to be the prime squared, because everything less than, uh, for example, everything less than 5 squared is going to have a factor of something smaller than 5 in it. Uh, so we'll start with 25 to the s plus, um, and then uh, we don't want factors, we don't want multiples of 2, we don't want multiples of 3, um, which means our next one is going to be 5 times 7, so that's 35 to the s, and so on. Now, if we factor this, let's see, um, we get 1 over 2 to the s times um, 1 plus um, 1 over 2 to the s, 1 over 3 to the s, um, let's see, um, where, where is the chat for this video? Should be somewhere. Oh, I guess I'll have to figure that out later. Um, but let's see. Um, uh, okay, so this is kind of strange. Because that's just our function again, the zeta. Um, uh, so let's take a look at why this is true. Um, hmm. Okay, let's try approaching it from the other way. So we have the product of 1 over 1 minus p to the negative s for p prime. And that's going to be 1 over 1 minus 2 to the negative s times 1 over 1 minus 3 to the negative s times 1 over 1 minus 5 to the negative s, and so on. So one thing I do remember is that 1 over 1 minus x, this is the um, uh, expression for the infinite sum uh, of uh, x to the n. But x has to be between -1 and 1. All right. So what this is saying is this is 1 over 1 minus 1/2 to the s times 1 over 1 minus 1/3 to the s times 1 over 1 minus 1/5 to the s, and so on. So all of these numbers here fall within that zone. So we can actually rewrite this as a product of infinite sums. I don't know if that will be productive, but we can try it. So we have that this is the sum of 1/2 to the n, and then we're multiplying that by the sum of 1/3 to the n, I'm multiplying that by the sum of 1/5 to the n, etc. Okay, okay. I'm starting to see it now. I'm starting to see it now. Because when we write this out, we get um 1/2 plus 1/4 plus 1/8 plus, and you keep going. And then we're multiplying that with the powers of 3, so 1/3 plus 1/9, that's a 9, plus 1/27, and so on. And we're multiplying that with the powers of 5, and so on. So we can get all of the composite numbers this way, because uh, I guess these should be zeros. My mistake. Which means there's actually an extra one in all of these terms, which is important. That is important. Um, okay, so we can get all of the numbers this way because well, if in order to get one, we just take all of the ones. And yes, there are infinitely many of them, but we uh, one times itself an infinite number of times um, is going to still be one. Um, and um, we can do the same thing with 1/2 uh, by choosing 1/2 to start, and all of the others were one. And we can choose 1/3 by choosing 1 times 1/3 times 1, and so on. And 1/4, it's that one, right? 1/5, it's that one. Now, 1/6 is where we start having to combine these. So it's 1/2 times 1/3, and then the rest are ones. Um, and then 1/7 is somewhere over there, right? Um, but you can start to see why this is true. Why the zeta function um, equals the sum of uh, um, n equals 1 to infinity of 1 over oh sorry uh yeah, 1 to infinity n to the s, y that equals the product of uh 1 over 1 minus p to the negative s for p prime. um okay okay. um so another thing um is that uh another thing we know about this series is if we let s equal 1, then we have the series 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, etc. And we know for a fact that this sum goes to infinity. It doesn't look like it does, but it does. Um, because, well, 1, that's greater than or equal to 1/2. 1/2, that's greater than or equal to 1/2. 1/3 plus 1/4 is greater than or equal to 1/4 plus 1/4, which is greater than or equal to 1/2. And then 1/5 plus 1/6 plus 1/7 plus 1/8. Well, that's going to be greater than or equal to 1/8 plus 1/8 plus 1/8 plus 1/8, which is equal to 4/8, which is equal to 1/2. And we can continue doing that. Um, so in order to define zeta of 1, we need a different way of um, calculating the result, because um, zeta 1 does exist. Um, and in fact, let's see if I can find a good picture of it. Uh, oh yeah, here it is. Okay, so what happens at 1 is that uh, it it looks like this graph, except it stops at 1 from the right. So everything to the left of 1 is just um, gone, because it goes to infinity as far as we can tell at the moment. Um, but the shape, the shape of the graph suggests there is a way to continue it past 1. Um, because if we make f any greater than 1 at all, we could make s equal to 1.00000000001, and it would still converge. But as soon as you hit 1, it doesn't, um, which implies that maybe there's a way to continue it past 1. Um, so we have something called a functional equation, and which allows us to define the function in terms of itself, but shifted. So, for instance, if we find that zeta 1 equals something in terms of zeta 2, and we know how to calculate zeta 2, then we can figure out what zeta 1 is. Um, so let's see, where is that functional equation given? Ah, here. Um, let's see. Okay, um is there another one? Um, hmm. Okay, so it seems like there's a pole at s equals 1. So it does actually uh, equal, it does actually go to infinity. It does actually go to infinity there. Okay, so um, this functional equation. Um, uh, so what 1 minus s does is if s is greater than 1, um, then zeta is calling a negative. Oh, I see. So if s is less than 1, or I guess it would have to be less than 0. If s is negative, then uh huh. Why does it say between 0 and 1 then? Um between 0 and 1. Um uh so let's see. Um so if the real part of s is a complex number, so it has a real and part and it has an imaginary part. Um if the real part of s is between 0 and 1, uh how does that help us? Because on 1 minus that would still be between 0 and 1. Uh, oh, I see. Okay, so 1 may define for all remaining non-zero complex. So for s less than or equal to, for the real part of s less than or equal to 0 and s not equal to 0, we can apply this equation outside of the 0 to 1 strip, which, by the way, is called the critical strip, uh, because that's where we don't know if there are um, any zeros of this function um, that don't have real part equal to 1/2. Um, uh, so that's called the critical strip. Um, but we can still apply this functional equation outside of the strip to get all of the negative values too. So uh, we get um, zeta. Yes, we're trying. There we go. Um, Zeta s equals um, 2 to the s pi to the s minus 1 sine of pi s over 2, and then gamma, capital gamma, 1 minus s, whatever that is. I've seen it before, but I don't remember exactly how it's defined. Um, and then zeta 1 minus s. Um, so let's take a look at the gamma. Oh, that's right. The gamma function is an extension of the factorial function. Um, and it's not defined at the negative integers. Um, okay. Okay. So we have um, gamma of z is equal to the integral from 0 to infinity of t z minus 1 e to the negative t dt. Okay. Um, and let's see, we can rewrite this as the limit as n approaches infinity of the integral from 0 to n t to the z minus 1 e to the negative t dt. Um, okay, so I'm, oh, that's right. So for every positive integer n, it equals n minus 1 factorial. Um, and let's see, I'm fairly certain that this integral is actually irreducible because they just have it written as the integral. If it were reducible, I assume they would uh, write the reduced form. Um, so uh, let's see. Um, gamma function can be seen as a solution here. Um, so this is the main definition. Um, Verges absolutely. Euler integral of this. Um, the beta function. Oh, okay. Um, oh, this is useful. Um, so we also have that gamma of z plus 1 equals z gamma z. Um, and that appears to work for all complex z. Um, so let's see, how does this help us? Um, okay, so one thing that um, occurs to me is that um, zeta 0 can't exist um, because there's a simple pole at s equals 1, and this functional equation is defined with the zeta 1 of 1 minus s. So then zeta of 1 would have to be defined. But there's a simple pole at s equals 1. So it's not defined. So zeta 0 is also not defined. Um, but it should work for all other um, s. Um, Now, another thing that I don't have um, a uh, solid grasp on is um, like so far we've only been looking at real numbers and even integers. Um, uh, oh, I see. So what I said earlier about zeta 0 not being defined was false. It is defined as negative one half. Um, oh, that's right. Okay. Um, yeah, that makes sense. Okay. So zeta 0 is negative one half. And what I what I want to look at um a bit further uh is uh what happens when we introduce complex numbers. So like what is um zeta of I? Um so theoretically that would be 1 over 1 to the I plus 1 over 2 to the I, 1 over 3 to the I, etc. Um, Now, uh, but like, what are we expecting when we raise something to an imaginary power? Um, well, we know that e to the I pi is negative 1, okay? Um, so this is something raised to the I power. Specifically, it is uh, e to the pi to the I equals negative 1. Um, and so if we say want to change the base of this exponential equation, um, we can, uh, I guess we would be, hmm, well, let's see. E to the pi to the I, negative 1. Um, oh, right. Okay. So if we want to change the base, all we got to do is change the power here. Um, so uh, which will effectively change the angle. Since this is actually something called polar form. Um, so uh, e to the pi I, well, that would be um, uh, so pi is the angle, um, and then what's out in front, which is 1 in this case, is the radius. So it literally just points to -1 here. But if we say change pi to log 2, uh, so e to the log 2 to the I, well, that would equal 2 to the I, um, and log 2 is going to be um, less than uh, less than 1, or yeah, less than 1. Um, and so I think it's going to be something like this, where it has an imaginary and real part to it. Um, and then we're also, so what we're doing is we're taking 1 over 1 plus 1 over um, e to the log 2 to the I, plus 1 over e to the log 3 of I, plus 1 over e to the log 4 of I. Um, and we're just doing that to ad infinitum. Um, so what we're looking at actually is a sum of specific points on this circle. Um, and then if we had a real part, instead of just evaluating at I, that would change the radius of the circle. But we're just looking at um, zeta of I right now. And we're doing this an infinite number of times. Uh, so, and we're adding all of these, adding an infinite number of arrows of length 1. Um, so the result, I would think, is um, infinity, but I'm not sure because some of these arrows may cancel um, most of the way with others. Hmm. I'm starting to see why the real part matters so much, though, because the imaginary part just determines where you are on the circle, right? Um, the real part, so the imaginary part determines the angle. The real part is what determines the radius. Um, and if you have s, the real part of s greater than 1, then the radius of these, the length of these arrows is going to decrease, such that the sun converges, right? Um, all right. Um, so let's see. Uh, hmm. Wonder. Let's see if we can evaluate some of these explicitly. Pull up Wolfram Alpha here. Uh, let's see if zeta I has a value. It does. Okay, so it's not infinity like I thought. Um, so it looks like it's a um, zeta I is roughly equal to 0.0033 minus 0.41816 I. Okay, okay. But in order for the zeta function to equal 0, we need both the imaginary component and the real component to be equal to 0. Um, uh, which I uh, since the imaginary component only determines the angle on the complex plane, um, and no two arrows no can completely um, cancel each other out because of the way the zeta function is defined. Um, so we we know for a fact that the reals uh, greater than 1, there are no zeros there. Um, and because of the um, way the functional equation is defined, the gamma function is never 0. Um, 2 to the s is never 0. Pi to the s minus 1 is never 0. Um, Sine, uh, we'd really only have to be worried about sine. Um, but if um, the and then but sine, we'd really only have to be worried about sine. Um, so how do we know that sine is not 0? Um, because I feel like if we made S equal to negative um uh negative 4, shouldn't the sign be 0? Yeah, if S is a negative even integer, then zeta S equals 0 because the factor. Okay, so they're the trivial zeros. Okay, right. So it does have a bunch of trivial zeros at the negative even integers because of this um, sign in the middle. So S equals negative 2, S equals negative 4, S equals negative 6. Um, the zeta function will be 0. Um, but these are the trivial zeros because we know everything there is to know about them already. Um, where we're interested, what we're interested in is um, so if we take out those zeros, if we don't consider them, then sign um, is never 0 in that context, right? Um, which means zeta 1 minus s would have to be 0 for zeta s to be 0. And um, that means that since we know that zeta 1, uh, anything greater than zeta 1, so zeta 1.01, zeta 1.0001, whatever, um, those are never 0. So anything less than 0, for any s less than 0, we know likewise, um, except for the trivial zeros, of course. Um, so that is why we're so interested in the real part of f being between 0 and 1. Okay, now um, the hypothesis conjectures that um, all of the non-trivial zeros have real part equal to 1/2. Okay. Um, so this one, that that is a lot more restricted than this constraint. Um, okay. So I'm starting to understand the constraints a bit. Um, now what I'd like to understand more about is how this function behaves. Uh, so looking at this, um, uh, this doesn't, um, Okay, right. So this is the function output, but I don't know what the inputs are. Um, uh, so I'd like to be able to visualize what's going on here. Um, so since we're so interested in the zeros of this function, actually, why are we interested about the zeros? What do the zeros tell us? Okay, what do the zeros tell us? Um, well, if this, if we take a look at the Euler product here, the um, zeta s equals the product of primes, 1 over 1 minus p to the negative s. So if the zeta function is 0, um, between real part 0 and 1, then that would mean, I think, that one of these components has to be 0 because the complex numbers form a field, right? So we don't have 0 divisors. Um, and if one of them can be 0, um, okay, why do we care so much about the zeros of this function? All right, so Euler, Riemann, number of primes less than or equal to given number x. Um, formula was given in terms of a related function. Pi of x plus 1/2 pi of x counts the primes and prime powers up to x. Um, counting a prime power p to the n as 1 over n. Number of primes can be recovered from this function by using Mobius inversion. Wow. Okay. Um, primes can be recovered from this function. Okay. So we have this Mobius inversion formula. Whatever. Okay. So it's just it looks like it's just kind of the inverse of the capital pi of x. Um, and we have um, I'm going to go over the non-trivial zeros of the zeta function and where capital Pi naught is a slightly modified version of capital Pi that replaces its value at its points of discontinuity by the average of its upper and lower limit. Um, so okay, what is Li? What is Li? Um, Li, Li. All right, I need to know what this Li means. Oh, it's given here. Okay, so we have um um Li of x is equal to the integral from 0 to x of dt over log t. Um, so this uh, pi, capital Pi naught, capital Pi naught is equal to the integral from 0 to x um, of dt over log t uh, minus the sum over uh, oh wait, sum is over the non-trivial zeros of the zeta function. Wow. Okay. So rho is a non-trivial zero of um, zeta s, and we're taking the sum of uh, the integral from 0 to x to the rho um, of dt over log t. That is insane. Um, and then we're doing minus log 2, and then we're adding this integral here, x to infinity of dt over t times t squared minus 1 log t. Wow. Okay, so the reason um, values at its point of discontinuity. by the average of its upper and lower bound limits. So, wait. Oh, I see. So, capital pi of x is discontinuous at x equals 0. So, capital pi naught of x um, will be the limit as epsilon approaches 0. And then um, this is capital pi as it approaches from the uh, left, and then this is capital pi um, uh, as it approaches from the right. And then we're just taking the average of those two values. Um, so that we have something at 0. Um, and um, so we we can calculate Li of x numerically. Um, that's not a problem. Um, and same with the other integral. We can calculate that numerically. The only sticking point then is the summation there. And that's why we need the non-trivial um, zeros of the zeta function. Okay. And so what happens if the hypothesis, the conjecture is true? Um, well, then that, remember that the real part said something about the length of the arrows on the complex plane. So going back here, um, if we have real part 1/2, um, well, that means um, our arrows are um, getting smaller each time, right? Um, so it will converge because, um, well, for one, even when the arrows are not decreasing in length, it converged. Um, but with the arrows decreasing in length, it will definitely converge. And the hope is that if it turns out to be 0, all the arrows cancel out, leaving us with just 0. Um, then what? Um, it says something about the distribution of primes. Um, uh, so let's see. The terms of the sum over the zeros of the Riemann zeta. Magnitude of the oscillations of primes around their expected position controlled by the real parts of the zeros of the zeta function. Oh, so we know a general distribution of primes, like an average, if you will, and that is it was shown to be um, um, log log x. Um, I think, yeah. So the reason why you see intervals with 1 over log is that the the 1 over log, is the distribution of primes. That was proven. Um, uh, so then, right. So based on the 1 over, based on the log uh, function, um, then we have an expected position for where the primes are going to be, and then the real parts of the zeros of the zeta function um, tells something about the magnitude of how far away from that expected position they will be. Um, so if we know the real part of S is equal to 1/2, um, then we know we are given a bound for where um, the that prime will be, and it's a pretty restricted bound, actually. Um, so uh, the best possible bound of the prime number theorem, highest version. Okay, so pi of x, that is the prime counting function, and Li is the logarithmic interval function. Um, and this is the bound, um, assuming the Riemann hypothesis. So if there are no zeros, non-trivial zeros, that have a real part not equal to -1/2, then this is true. Um, and uh, okay, so at some point I will want to look at why, but I am nowhere near that level yet. Um, okay. Uh, it also means that um, if we can find a counterexample to this, um, to this pi of x minus Li of x, um, then it would disprove the Riemann hypothesis, which would be wild. Um, but so yeah, let's see. All right, let's go down to here. What is the argument principle? Okay. It's the theorem in complex analysis. The argument principle is a theorem relating the difference between the number of zeros and poles of a meromorphic function. Meromorphic just means that it is um, analytic or infinitely differentiable at everywhere except a um, countable set of points. Um, we're doing this to a contour integral to the function's logarithmic derivative. Um, okay. Um, all right. So functional equation combined with the argument principle implies a number of zeros of the zeta function with imaginary part between 0 and t is given by. Uh, okay. So we get between 0 and t with imaginary part between 0 and t. Um, so we're assuming the real part is between 0 and 1, right? Um, actually, we're assuming the real part is 1/2, um, I guess. Um, okay. Um, so the density of zeros with imaginary partner t is about. Okay, I am a bit lost here. Um, so let's back up a few steps. Um, so if we go back to the consequences, um, we'll see. I want to look into how these were determined. Um, so actually, I want to go to Riemann's um work, start from the historical beginning. Um, so uh, written in German. Um, let's see. Um, so sorry, I'm gotten a bit quiet. Uh, trying to find. Uh, so we figured out how Euler um, um, converted it to a statement about primes, right? So where this formula is coming from, right? Um, Now we want to know, why do the zeros of this function defined in the complex plane tell us something about the distribution of prime numbers, which are integers. Um, so the actual paper is written in German, so uh, English translation. Uh, is there an English translation that I can read? Um, Here. Okay. Um, so we have this. Um, if one substitutes for p all prime numbers and for n all whole numbers, function of the complex variable s, which is represented uh, p all prime numbers, n all whole numbers. Right. Okay. Function of the complex variable s, which is represented by these two expressions, wherever they converge, is zeta s. Both expressions converge only when the real part of s is greater than 1. Um, okay. Both expressions converge only when the real part of s is greater than 1. Yeah. At the same time, an expression for the function can easily be found which always remains valid when making use of the equation this thing. Okay. So the integral from 0 to infinity of e to the negative n, excuse me, x to the s minus 1. Um, all right. So we have, um, I kind of want to know where that equation is coming from, but we'll stay focused here. 0 to infinity of e to the negative nx, x to the s minus 1 dx. Um, that equals, um, oh, the capital pi function. Okay, it's a bit confusing here, because uh, we have a capital pi here, which is different from the capital pi here, I think. Uh, this capital pi is referring to a function. This is a series of operations. Um, so um, the capital pi of s minus 1 over n to the s. Um, okay. And we determined from the Wikipedia article that, what was capital pi? Oh, I didn't write it down. Um, Capital Pi um, of x is equal to lowercase prime of x plus 1/2 pi, pi of x to the 1/2 plus 1/3 pi x to the 1/3 and so on. Okay, and then little pi is the prime counting function. Um, so um, this makes a certain amount of sense to define a function like this, um, because you're how to articulate that. Um, like, what is this function actually doing? It is um, taking the number of primes uh, below x, adding to that um, 1/2 times the number of primes below the square root of x, adding to that 1/3 times the number of primes below the cube root of x. And um, eventually, um, since x is our argument, that's staying constant, all right? Um, Eventually, if we take x to some high enough 1 over nth power, so like 1 over a million, um, eventually the number of primes below that value is going to be 0. So it may look like there are an infinite number of terms here, but there are actually finite number because there will be an infinite number of zeros. Um, which means this function should always converge, I would think. Um, yeah. So if we go back here, let's see. So we have this complicated looking integral. That's going to be uh, capital pi of s minus 1. Now, one thing that worries me a little bit is s is a complex number, but x here in this definition is a natural number, right? Because we're counting the number of primes below x. Or I guess it can be a positive real number too. Uh, but like if we plug in I to this thing, how many primes are below I? That doesn't even make sense. Um, so there must be an explanation for that discrepancy. Um, let's see. Um, Only when the real part of s is greater than 1. At the same time, the expression function easily be found, which always remains valid. Uh, yeah, that's something I don't understand. Um, how is it using complex numbers here? Um, maybe they're using a different definition of capital pi. Uh, um, which I want to, because there's context there that I'm missing. So I want to figure out what this capital pi is if it is taking in complex numbers as an input. But yeah, so uh, formula was given. Um, okay, so yeah, I'm confused. Mm, okay, hold on. If we take a step back and consider this a definition rather than uh, a derivable equation, um, that would mean that uh, capital pi of um, s, I'm going to change the variable slightly here, replace s minus 1 with s, um, equals, um, now we had a uh, n to the s, but we replaced s minus 1 with s, so this will be s plus 1 equals this integral here, e to the negative nx, x to the s, dx. Um, and so then our capital pi of s equals n to the s plus 1 times the integral from 0 to infinity of e to the negative nx, x to the s dx. Okay, so this, if we use this as a definition, right, what is going on here? now the zeta function suddenly shows up. Um, Zeta function suddenly shows up. Uh, oh, right. So instead of n to the s, we're replacing it with the sum of 1 over n to the s to infinity. Um, so what we're effectively doing, okay, so that is why it was in terms of s minus 1 before. Um, okay, that makes sense. That makes sense. Um, so we have capital pi of s minus 1 equals over n to the s equals the integral from 0 to infinity of um, uh, e to the negative nx x to the s minus 1 dx. Um, okay, so now instead of 1 over s, we're going to be um, I guess are we summing? No, wait. Okay, so I'm just gonna rewrite this integral here, 0 to infinity of x to the s minus 1 over e to the um, nx dx. Okay, so where is the minus 1 coming from in that second equation? Wait, hold on. Okay, wait. Um, so I'm gonna rewrite this integral again. Um, x to the s minus 1 over e to the x to the n. Now, um, recall that uh, zeta s, that is the sum of 1 over n to the s from n equals 1 to infinity. Um, so if we say do this, um, then that is saying this is capital pi of s minus 1 times 1 over n to the s, or I guess 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, etc. All right. And then, oh, right. Okay. So then we can um, split this up into a a sum of, uh, here, I'll do it on a separate page here, capital pi of s minus 1 um, over 1 to the s plus capital pi uh, of s minus 1 over 2 to the s, etc. And from this formula here, um, we can replace it with the corresponding n value. So n equals 1, n equals 2, n equals 3, etc. Um, so then what we get is that this equals the integral from 0 to infinity of, we're just going to write this formula over and over again, x to the s minus 1 over e to the x to the 1 dx plus the integral from 0 to infinity of x to the s minus 1 over e to the x squared dx plus the integral from 0 to infinity of x to the s minus 1 over e to the x cubed dx, and so on. And we can actually, since these integrals have the same bound and the um, same, we're integrating over the same variable, we can actually combine them. So we get the integral from 0 to infinity of um, x to the s minus 1 over e to the x to the 1 plus x to the s minus 1 over e to the x squared plus x to the s minus 1 over e to the x cubed, and so on. Okay, now if we factor out, oh yes, 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 okay. If we factor out an x to the s minus 1, then we get the integral from 0 to infinity of x to the s minus 1 times 1 over e to the x plus 1 over e to the 2x plus 1 over e to the 3x, and so on. Okay, okay, this is starting to make more sense. Um, Now, how do we get from here to there? There. Um, hmm, wait. Okay, so if we let 1 over e to the x plus 1 over e to the 2x plus, and so on, equal to, uh, let's call it a, then what we're going to do is say this is 1 over e to the x, and then we're going to factor out an e to the x from the rest of it. So it becomes 1 over e to the x, and then this still has to be uh, 1 over e to the x plus 1 over e to the 2x plus, and so on. and that still equals A. All we've done is move some terms around. Um, which means uh, this this quantity here is actually the same thing as A. Um, so we know that 1 over e to the x um, plus 1 over e to the x times A equals A. And so um, if we put all the terms of A on the same side, um, we get 1 over e to the x equals